Analyze the continuous beam shown in figure by slope deflection method. Support B sinks by 8 mm. Take EI equals 15,000 kilonewton meter square. Here, this is overhanged portion subjected to point load. The span is 2 meter. This is A, this is D, and then here in span EB, it is subjected to a couple moment of 150 kilonewton meter in clockwise direction at this 2 meter each from either end. Then in this portion B to C, it is 5 meter. It is subjected to UVL or linearly varying load of 25 kilonewton per meter. At B it is 0, it is maximum at C. Then first you have to calculate. Here he has not given any EI, that means here he has not mentioned, that means the flexural rigidity EI is constant from D to C or throughout the length of the beam. First we have to calculate the sinking of the support. Here in span D to A there is no sinking. Here support B sinks by 8 mm with respect to its original position. Then here this is the sinking of the support. Here with respect to A, B is at lower level, or here the rotation is clockwise. Here the rotation is clockwise. That means here the delta is plus 8 mm or 0.008 meter. Similarly, for this span the rotation is anti-clockwise like this, or that is here with respect to its original position, it is with respect to B, C is at higher level, then delta is negative, that is minus 8 mm. That one is 0.008 meters. Now first step is calculate the fixed end moments, FEM. That is the first step. Now we have calculated the delta 1, delta 2 for different spans. Then MFAB equals here MFBA equals both the fixed end moments are same, that is M by 4. Since the couple moment is in clockwise direction, that is 150 by 4, that one is 37.5 kilonewton meter. In the beginning I have given the values, that is MFBC for the second span. Here it is subjected to UVL. This one is anti-clockwise, WL square by 30. That is W is 25 into L is 5 square divided by 30. That one is minus 20.83 kilonewton meter. Then similarly MFCB from the other end C, that is plus WL square divided by 20, or it is clockwise, that is 25 into 5 square divided by 20. That one is 31.25 kilonewton meter. Here there is no for the overhang. For overhang, convert that overhang into the resisting moment. For overhang resisting moment, convert that overhang into resisting moment. That is here the actual moment is, this one is point load of 20 kilonewton. This distance is 2 meter. This one is support at A. This one is D. This one is A. The actual moment is 20 into 2, but the resisting moment, that one is the resisting moment MAD. That one equals 20 into 2. That one is 40 kilonewton meter. That is clockwise. That is opposite moment. That is opposite moment. That one is clockwise, but the actual moment is anti-clockwise. Then the second step, write the slope deflection equation for all the spans. That is, first write the slope deflection equations for overhang. For overhang, no SD equation, no slope deflection equation. Then MAB, write the slope of deflection equation for MAB. Here the near end is A, the fixed end moment is 37.5 plus, here the fixed end moment is 37.5 that we have calculated, plus 2E. Here the flexural rigidity is constant. The length of this one is for 2 theta A, the near 2 times near end slope plus 1 times far end slope minus 3 delta by L. 3 into delta for this one is, that is positive 0.008 divided by L, that is 4 meter. This one by substituting the value of EI equals, that is given as 15,000. Then this one is 37.5, 2 into 2 4, 2 into 2 4 by 4 into EI is 15,000 theta A plus theta B, that is 2 by 4 into 15,000 theta B minus 3/4 of, that is 0.008, that one is 2 by 4 into 15,000 into, that is 3/4 of 0.008. Here by simplifying this you will get, this one is 15,000 theta A plus 7,500 theta B minus 7.5. Here you will get MAB equals, this is equation number 1. Here this one is equation number 1. Then MBA, here similarly we can write MBA, that one is 2 into EI is 15,000 divided by 4, that is 2 EI by L inside the bracket, that is 2 theta A plus here the near end is B, far end is A, minus 3 into delta, that one is 0.008 divided by L, that is minus 37.5, that is here plus 37.5. Since both are clockwise, the fixed end moments both are clockwise, then this one is by simplification you will get 7,500 theta B. I will write like this, that is 15,000 theta A, this one is theta B minus 7.5, this one is 7,500 theta A plus 15,000 theta B minus 7.5. This one is equation number 2. Now we can write the slope deflection equation for MBC, that is fixed end moment, that is minus 20.83 plus 2EI, that is here instead of EI I will write, that is 15,000 divided by length is 5 inside the bracket 2 theta B plus here the near end is theta B, far end is theta C, minus 3 delta, that is minus 0.008 divided by L. Then after simplification you will get MBC equals, that is 12,000 theta B. Here theta C equals 0, theta C equals 0 since that is fixed end, hence this one is 0, that is 12,000 theta B, 12,000 theta B minus plus 7.97, 7.97. This one is equation number 3. Then MCB equals, here In the same way we can write, that is fixed end moment is 31.25 plus 2EI, that is 15,000 divided by 5, that is length. Here the near end is 2 theta c plus theta b minus 3 into delta 2 divided by L. Then this theta c is 0. Therefore this one is 6,000 theta b, 6,000 theta b plus 60.05. Here after simplification we will get the equation like this. This is equation number 4. Now by solving these equations, that is 1 2 3 4, there are 4 equations we have got. Then by solving these 4 equations, that is by equilibrium condition, that is by equilibrium condition, we have to here next step, that is equilibrium condition. Here by equilibrium conditions, here at A, here at A, 2 members are connected, one is AD and another one is AB. Then that is summation MA equals 0. Summation of MA equals 0. That means here we have already calculated, that is resisting moment in portion AD, that is overhanged portion, plus MAB, the summation of these two equals 0. Here we have just now written the equation for, that is MAB equals, that is here we will get, that one is here 15,000 theta A plus 7,500 theta B. Here 32 point minus 40 plus 7.5, that is 32.5, that one is minus, here this is equation number 1. Here we will get an equation, that is simultaneous equation. Then similarly at joint B, again summation of the moments equals 0 at that joint. Again there are two spans, that is 2 spans are, one is MBA, that is BA is one B, BA is one span, BC is another span. The summation of these two equals 0. That give us, here by adding MBA, MBC, just now we have calculated, we have written the equation, that is 7,500 theta A, that one is 7,500 theta A. Then 12,000 plus 15,000, that is 27,000 theta B, 27,000 theta B. Then 7.97 plus 7.97 minus 7.5, that one equals minus point, that equals minus 0.47. This one is equation 2. Here theta A is one unknown, theta B is another unknown. There are 2 equations. Then we can solving these 2 equations, that is by solving the 2 equations 1 and 2, by solving simultaneous equations 1 and 2, then we will get the unknowns, that is theta A and theta B. Theta A equals, that is by solving this equation, theta A equals, that is minus 2.506 into 10 to the power of minus 3. Similarly theta B equals, that is 6.788 into 10 to the power of minus 4. Then here after getting the values of theta A and theta B, then the final moments we can get by substituting these values of theta A, theta B, substitute these values in SD equations, slope deflection equations, what we have written, that is 1 to 4. Then here we will get, already we have got the value of MAD, that is MAD equals 40 kilonewton, that is kilonewton meter, that one is clockwise. Then MAB, here we have written the slope deflection equation for MAB, that is here by substituting the values of theta A, theta B and theta C, then this one is minus 40 kilonewton meter. That one is minus, means that one is anti-clockwise. That one is anti-clockwise. Then MBA, by substituting the values of theta A, theta B in the above equation, that is minus 16.11 kilonewton meter. Minus means that one is 16.11 kilonewton meter in anti-clockwise direction. Then MBC, that one is 16.11 kilonewton meter in clockwise direction, that is positive, that means that is clockwise direction. Then MCB at fixed end, the moment, that one is 64.12 kilonewton meter. Here, after knowing the values of the fixed end moments, now we can draw the bending moment diagram for this one. That is, here for this beam we can draw the bending moment diagram, that is BMD, SFD. We can calculate BMD and SFD. Here this beam is, that is overhanged at one point in one portion, that one is here, this one is overhang in this portion, this one is support E, this one is D, this one is A, this one is 20 kilonewton, this one is 2 meter, this one is a couple moment, that is a couple moment in clockwise direction, that one is 150 kilonewton meter, this one is 2 meter, this one is also 2 meter, this one is support B, this one is support C. Here it is subjected to UVL, that is linearly varying load of intensity. Here it is 0 at one end and maximum at the other end. This one is 25 kilonewton meter. Now we have calculated the values of the moments, that is theta A equals, this one is slope at A, the slope MAD, that one is clockwise, that one is 40 kilonewton meter in clockwise. MAB, that one is anti-clockwise. Here this one is minus, that is 40 kilonewton meter. This one is the moment at this support. Then the moment at this support, that is here, just now we have calculated here MBA, MBC, this one is 16.11 kilonewton meter. This one is the moment at this support. Similarly, at this support here, this one is 16.11 MBA, that one is clockwise, that one is clockwise. Then that is like this. Here MBC is anti-clockwise, that is like this. Here MCB, that one is clockwise, that is positive. Then this one is the moment at this end, this one is 64.12 kilonewton meter. Here now we have got the moments at support. Now we can draw the bending moment diagram for this one. Here consider this one as the reference line, this one as the reference line for this one. Here this one is the bending moment is 0 at this point. Here the support moment is, that is 40 kilonewton meter. Here with respect to the reference line, here by observing these two moments, both are sagging moments, hence we will represent the sagging moments above the reference line. And then here by observing this span, the moment varies from 0 to maximum value, hence join the 2 points. This one is 40 kilonewton meter. Here by observing this, the shear bending moment is sagging. Here to differentiate hugging and sagging bending moment, we will consider this moment in downward direction. If you take it above the reference line, there is no difference between hugging and sagging. Hence to differentiate these two moments, here I have shown this moment in downward direction. This one is 40 kilonewton meter. This one is 40 kilonewton meter. This one is 16.11 kilonewton meter. This one is one of the support moment, that is sagging. Then here this one is hugging again. Here at this point the moment is hugging, hence we will consider this moment above the reference line like this. Then join this point with that point to get the support moment diagram. Here this is the support moment diagram. This is the support moment diagram what we have calculated just now, that is the support moment diagram. Here this one is negative, this one is positive, this one is negative. Then here span moments, in this span the moment varies from 0 to 40 at the support. Here the support reactions due to this couple moments, we may consider this one as a simply supported beam subjected to couple moment. This one is 150 by 4, that one is 150 by 4, that one is 37.5 is the support reaction. This one is this moment is 30, that's this support. Here this one is 37.5 into 2. Here there are two moments, that one is, here this one is negative bending moment due to the simply supported beam bending moment. This one is 37.5. The support reactions are 37.5 each, 150 by 4, that is 37.5. 37.5 into 2, that one is 75 kilonewton meter, that is hugging bending moment. Then here this one is again 37.5 into 4 into 2, that one is sagging bending moment. This one is positive bending moment. Then here in this portion at support the bending moment is 0 due to simply supported beam bending moment. Then here this one is the curve, that is if you consider this one as a uniformly varying load, that one is third degree curve, that is variation is a curve, that is second degree curve or parabolic. This one is parabolic variation. Then this one is, here this is 150 kilonewton meter. Here this one is negative bending moment, this one is negative bending moment, this one is also negative bending moment, this one is also negative bending moment, this portion is positive bending moment, this portion is positive bending moment, then this portion is negative bending moment, this portion is positive bending moment, this one is again positive bending moment in this portion. Here now we can show this bending moment diagram by hatching like this. This is the net bending moment diagram in this portion, that is purely negative bending moment. Similarly in this portion here, that is here in this portion, that is positive bending moment. Here this is the bending moment diagram for this one. Here the maximum bending moment occurs, that is we have studied in strength of material, that one is the maximum bending moment is 0.00 0.064 WL square. This is the maximum bending moment. This is the maximum bending moment due to UDL. This is the bending moment diagram. Then to draw the shear force diagram, here now we will consider summation of V equals 0, that give us here, this is VA plus VB plus VC, the sum of all those things equals, that is here 20. Then this one is half of 5 into 25, that one is here VA plus VB plus VC, that equals 20 plus 25 into 5, that is 125 by 2, 62.5. This one is 82.5 kilonewton. 82.5 kilonewton you will get. Then by considering the moments of all the forces, here we will consider only this portion. Only this portion, that is summation of MB equals 0. Summation of MB equals 0, that is only LHS we will consider. Then we will get by taking the moments, that is VA into 4, VA equals 1 divided by 4, that one is the clockwise moment. Then by equating clockwise moment and anti-clockwise moment, that is 20 into 4 plus 2, that is 6, that is 20 into 6, that is anti-clockwise. Here we have we are calculating the clockwise moment by equating clockwise moment and anti-clockwise moment. Here the summation of these two moments is 0. Then this one is minus 150, that one is clockwise moment. Then this one is anti-clockwise moment plus 16.11 kilonewton meter. Then VA equals, here by equating this, VA equals, we will get, that is VA equals minus 3.47 kilonewton meter. That one is negative, means VA is downward, 3.47 kilonewton in downward direction. Then here summation of MB equals, by closing this portion, by taking moments of all the forces about C, here we will consider only RHS portion. That one is here, this one is VA, VB, VC into 5, that one is VC equals 1 over 5. This one is anti-clockwise moment. Equate this to the clockwise moment. Here by closing this one is anti-clockwise minus 16.11. Start from this point, moment to this VB is 0. Then this one is, that is here, this one VC into, this one is VC into 5. This one anti-clockwise moment, that is clockwise moment 16.11. Here this one is anti-clockwise. Then this moment is also clockwise, that is 64.12. Then moment to this one, that one is here, that one is half into 25 into 5. This is the total load which is acting at a distance of 1/3 of 5. Then here by equating this, here moment to this one, and this one, and moment to this one, there are 1, 2, 3, 4. Then VC equals, here by calculating this one, we will get the value of VC equals 57.71 kilonewton. This one is upward, that is positive. Then here by equation 1, by equation by equation 1. By equation 1 you will get Vb equals, by substituting the value of Va and Vb equals, that is 28.26 kilonewton, that is upward, that one is positive. Then now we can draw the shear force diagram for this one. That is, the shear force diagram for this one is here. This one is the shear force diagram. If you consider this one, this is the, here I will draw the shear force diagram in this portion only to complete this. Here this is, here this one is subjected to point load, this one is subjected to a couple moment like this. Here Va is downward, that is Va, that one is minus 3.47, that is downward. Then this one equals, here this one is 20 kilonewton, this distance is 2 meter. Then this one is couple moment 150 kilonewton meter. This one is Pb, that one is just now I have calculated, that one is 28.26 kilonewton. Then Vc, that one is 57.71 kilonewton. Here this is subjected to UVL like this. Here to draw the shear force diagram for this one, from left, start from left, that is here the shear force diagram for this one is, it is like this. Here this one is, here left upward is positive, left downward is negative, this one is minus 20, it remains constant up to this point, that is 20. Then again there is a reaction at A, that is in downward direction. This one is minus 20, this one is minus 20, minus 3.47, that one is minus 23.47 kilonewton, this one is kilonewton. Here this one is negative shear force. Here the shear force due to the couple moment will not change, it remains constant up to B. Then here there is a reaction at this point, that one becomes here, because of this reaction at B, the shear force will change, that is 23.47 plus 28.26, then the shear force becomes, that one is 4.79 kilonewton, that one is 4.79. Then here the shear force variation is curve like this. Here the shear force variation, it will change like this, that is second degree curve or parabolic like this. Here the shear force variation, this one is positive, this one is positive, this one is 4.79, then this one is 57.71, this becomes 0, this is A D, this one is A, this one is B, this one is C. Here this is the shear force diagram for this one. Here this completes with this problem. We'll continue in the next video.